This is exercise 1 of the physics final project. In this exercise, we have to find the following quantities for a raindrop and a baseball. The critical velocity, the terminal velocity, time it takes for the body to reach terminal velocity, and distance the body has traveled, okay? So, first, our critical velocity is the viscous term equal to our drag term v squared. Now in this case, since we're dealing for two spherical bodies, which is a raindrop and a baseball, we have that critical velocity is equal to our first drag coefficient times radius times velocity equal to our second drag coefficient times radius squared times velocity squared. Now C1 and C2 are values we already have that are given from our final project guide. And it's also important to understand that the viscous term dominates for speeds smaller or equal than our critical velocity divided by 10, and that our drag term velocity dominates for speeds bigger or equal than our critical velocity times 10. So now that we've understood critical velocity, we can solve for both v's circled in red. Those v's are the critical velocity. If we solve for them, we have c1 times radius over c2 times radius squared. So first, let's find our critical velocity for the water drop. That is 3.1 times 10 raised to minus 4 kilograms meters per second times the radius, that is a given value, divided by 0.87 times the radius, 2 times 10 raised to minus 3 squared. If we enter the given values in a calculator, that'll give us 0.178 meters per second. Now, if we solve for the baseball, we have to do the same. So the values are 3.1 times 10 raised to minus 4 times the radius, which is 7.5 times 10 raised to minus 2 divided by the second drag coefficient, which is 0.87 kilograms meters raised to 3. Okay, this is something I didn't mention for the water drop. Here we have, in this area over here, we should have kilograms over meters raised to 3. So here, if we finish it off, we have 0.87 times the radius squared, 7.5 times 10 raised to minus 2 squared. If we solve for this, this will give us 0.0047 meters per second. So now that we've finished the first exercise, it's time to find the terminal velocity for both objects. So if we want to find out the terminal velocity, it's important to understand that the sum of forces that happen along the y-axis. Okay, we have our drag term minus the gravity force. Okay, this is equal to mass times acceleration. Now, since we want to find the terminal velocity, mass times acceleration will be equal to 0, because once we reach the terminal velocity, there will be no more acceleration. It'll be a constant velocity. So the formula for each of these variables is 1/2 times c, a drag coefficient, times the density of our object, times a, which is the cross-sectional area, times v squared, which is our terminal velocity. This minus 4/3 times pi r3 times the density times gravity. Okay, now this formula came out of the volume for our sphere. Since both objects are spheres, we won't have much trouble with those formulas. So yeah, if we solve for our Vt, which is terminal velocity, we'll have that V term is equal to 2 times the force of gravity over c times density times cross-sectional area, all this in root squared. Okay, so this is the general formula we'll be using for both objects. So if we enter our known values in the previous formula, we will find out the terminal velocity for our water drop and for our baseball. For the third exercise, we have to use the values found on exercise number 1, where we got our critical velocities, and based on those velocities, we have to use a rule of 3, where we use those velocities to find out the distance the objects have fallen and also the time it took them to reach the critical velocities.
Exercise 2, Part 1. Find an expression for the terminal velocity. First off, we are presented with this expression, which is mass times gravity minus the drag term times the terminal velocity squared equals 0. Now, in order to get the expression for the terminal velocity, we have to first add d times v squared to both sides, then divide by d, and then take the square root in order to isolate the terminal velocity. And this is our final expression. For part 2, we are presented with two items, a ping pong ball and a lead ball, which both have the same physical size but different masses. And the question is asked, which one of the two items will have the biggest terminal velocity? Now, the drag term contributes opposite of motion, and therefore, the bigger the drag term is, the smaller the velocity will be. The opposite is true for the mass, because we have mass times gravity, which is also known as the weight, and the weight is always centered downwards to the center of the Earth. Now we can prove this mathematically by putting in terms. For the lead ball, I proposed 2 kilograms, and for the ping pong ball, 1 kilogram. Therefore, the lead is bigger than the ping pong ball. I also decided to plug in a value of 1 for the drag term, and since it's the same for both balls, as they have the same circumference, I plugged it in the same for both equations. Now, if we solve, after plugging in these values, we get 4.42 meters per second as a terminal velocity for the lead ball and 3.13 as a terminal velocity for the ping pong ball. Therefore, you can clearly see that the item with the lesser mass also has a lesser terminal velocity. For the third part of the exercise, we are given the situation of two different men falling out of an airplane in skydiving. We are told that the drag term is 0.03, and the first man weighs 50 kilograms, and the second one has a mass of 100 kilograms. Now, we simply plug in the values for each man on the equation established in the first part, and we get that the man with the mass of 50 kilograms has a terminal velocity of 127.8 meters per second, and the man with 100 kilograms of mass has a terminal velocity of 108.7 meters per second.
Exercise 3. Obtain an expression for the terminal velocity. Two objects with the same physical size but different mass, like a table tennis ball and a lead ball with the same radius, they have the same value of k but different values of mass. Who has the larger terminal speed, and hence who falls faster? You have to explain why. So, first we need to know that terminal velocity is the highest velocity an object can have as it falls through a fluid. So, to know this answer, we need to know that terminal velocity is the speed where the force of gravity pulling an object down exactly equals the air resistance acting against gravity. So the answer is, for instance, a tennis ball sphere will reach a much higher terminal velocity than a lead ball because the surface area of the tennis ball and therefore the resistance of the object to pass through the air will be much higher. It isn't just about density. A tennis ball will fall much faster than a lead ball because the latter has more surface area even though the material density is exactly the same, assuming the plate does not find a stable edge on descent. So, if we plug values in the formula that the exercise gives us and put, let's say, like 100 to the tennis ball and 500 to the lead ball, it will be a much higher terminal velocity for the tennis ball than to the lead ball.
In order to perform the experiment, we used a cylinder with marks every 1 centimeter in order to be able to calculate the position in Y when the marble is dropped. Being the distance of 30 centimeters, we used an application called Beauty Analyzer to analyze what position was the marble to respect with the time.
Exercise 6. This exercise we need to obtain terminal velocity. But in order to do that, we need to know what forces are acting upon our sphere, or marble, in the case of the experiment. When a solid sphere falls in a liquid, it has an accelerating velocity, but this is controlled by the viscous force, and it attains a constant velocity which is known as the terminal velocity. Shown by the drawing, we can know that the terminal velocity has an upward force, which is the upthrust, and the viscous force. This balances with the downward force, which is the weight. Knowing this, we can obtain the formula of this which is th plus viscous force equals to the weight, which means 4/3 of pi radius to the third times the density of the liquid, which is this, times gravity plus 6 pi the density, the coefficient of viscosity, in this case water, times the radius times the velocity equals to the weight, which is 4/3 of pi radius to the third times the density of the body times the gravity. By knowing our equation, we can solve for v, which is our terminal velocity, and give us a equation which is 2/9 of radius to the square gravity density of the body minus density of the liquid divided by the coefficient of viscosity. We know by researching that the density of the liquid, in this case water, is 1 gram per centimeters to square. The density of the body is the mass divided by the volume, which is our mass of the marble, 5.9 grams divided by the volume, and the coefficient of viscosity on water, which is 0.998, and the radius of our marble, which is 2.85.
By making the substitution for the velocity and knowing our quantities, we can make the equation knowing that the radius, which is 2.85 to the square times the gravity, which is negative, multiplied by the density of the body, which is the mass divided by its volume, minus 1, which is the density of the liquid, water, divided by the coefficient, which is 0.998. All these multiplied by 2 and divided by 9 give us a terminal velocity of 16.64 meters per second. How to determine the value of K? Knowing that the viscous force is the force between the fluid and a body, in this case the marble, and being given the formula for K, knowing that the coefficient multiplied by the radius, in this case the coefficient of the viscosity of water is 0.998, and the radius of our marble being 2.85, we can obtain the value of K, it's 2.84. By doing the experiment several times, we came out with 3 different graphs depending on the way we throw the marble and also the cylinder or the plastic bottle being used. So we could analyze the position of Y depending on the time. To a better realization of the experiment, we think it's better to have a smaller cylinder because the marble tends to move to side, so it's difficult for the video analyzer to analyze the information and give a specific position. So we think it's better to find a a narrower cylinder to do the experiment.